All right, you guys are here. I'm going to get started. Everybody else can watch the video to see what they missed. And the secret word today is the Chattelier's principle. Anyways, time to get started. All right, good morning, everybody. Time for another exciting morning of general chemistry with your host, me, Dr. White, in Chem 1211. And I hope you all have a good day today. It's really getting warm out there. Notice I have my short sleeve top on. It's almost the end of November. Speaking about that, next Thursday is Thanksgiving. Happy Thanksgiving almost. I hope you don't go to any big gatherings. I'm not going anywhere this year. It's a safe thing. I'm going to talk to someone. We may have a Zoom Thanksgiving dinner where we each sit in front of our computer and pig out, which should be fun. All right, important things. First of all, next Thursday, no class. Because of that, and I don't want to cheat you, because the more you spend time with me, the better your grade is. At least I hope it's true. We will be having class on Monday and Tuesday next week. If you can't make it on Monday, watch the video. On Monday, we'll start our normal time at 10 o'clock, and I'll be putting all this in an email to you. On Tuesday, because of a minor change in my physical therapy, which is doing wonders for me. Thank God for the people at NCH Group. Their physical therapists, Sarah, Peter, and Anita, are fantastic. So are their doctors and nurses too. But on Tuesday, just so I don't cut it too close, we will start at 10:30. And I'll put this in an email. Next Tuesday, we'll start at 10:30. On Monday at 10, we'll have a Zoom meeting class. Now, if you notice, I how should I put this? Wrote the wrong thing on the lab syllabus. I have no lab and then I have Thanksgiving. I just should have put no lab because next week we'll do the lab on Tuesday. That's scheduled for next week. This week's lab, which I postponed until Tuesday, is not due today, even though it might say that in the syllabus, or not the syllabus assignment, it's due on Tuesday. And with that, since I've totally confused you now, is there any questions? Well, with that, let's get going.
Dr. White, on Monday is going to be, how I understood correctly, the class, Zoom, and on Tuesday, right?
Correct. I'll say it again. On Monday, we'll have a class from 10 to about 11:45, like normal. And then on Tuesday, we'll have our class as we normally would, but it's going to start at 10:30. Since the net class, I can do this. If we're at ECC, wrong school, COD, we just wouldn't have a lecture on Thursday. But because the net class and I'm posting on video, I feel I can do this, and I can.
Thank you.
And it's really for your benefit. I wouldn't mind a day off, but it's more important that I spend time with you so you do good on the test and learn the material. All right, now, we're talking about the Chatelier's principle and its effect for exothermic and endothermic reactions. An exothermic reaction gives off heat, heat's on the right. Endothermic, you add heat. So let's do some examples. You've already done it, so I'm going to make you work now. Everybody see the whiteboard? Nothing on there but white. And me too, I'm white. All right, let me do one more thing. All right, first of all, let me remind you, ice bath removes heat and boiling water adds heat. So for this equilibrium, hydrogen gas, H2 plus Cl2, chlorine gas makes 2 hydrochloric acid gas, and this plus heat. Now, what happens to the concentration of hydrogen, HCl, if you add more chlorine? Or B, put the reaction in an ice bath, and C, put the reaction in a beaker of water. I'm going to let you try this first. Remember, with Chatelier's principle, equilibrium shifts to the side to remove or remove the heat, remove the stress. Where is everybody? Is today National I'm Bummed Out from everything going on day? So I'm going to stay home and not do anything? But that would have been this week, last week, and next week holiday. I hope not. All right, I'll let you do your work, then I'll do this. By the way, I got to get some of my favorite stuff at Benny's. One is Absolute Vodka. Dr. White loves his vodka. And the other thing which I also like is I got some good German wine, Pierce Porter, Golden Trocken, not Cabernet. I got the Auslese and Spätlese. I worked in that part of Germany at times, so I know about that wine. And then one of my also favorites is Di Serono Amaretto. Ooh, I like that too on ice. But if you're underage, put your fingers in your ears because you didn't hear what I said. Oh, that reminds me. I think I had my first drink of alcohol when I was 5. I was at my Grandpa Greenman's house or place, and my father and grandfather were drinking Canadian Club. I asked my grandfather, "What's that?" And he says, "It's good stuff." I said, "Could I try some?" And whoa, like you say, smooth. No, I didn't say that when I was 5, but I should have. Knocked me for a loop, and they laughed. He used to smoke cigars, and he did the same thing, and I learned not to smoke cigars that way. "Oh, can I try it?" "Sure." And I coughed my lungs out for a while. "No, I don't like that." All right. Anybody need more time? Give me a thumbs up if you're done. All right. I think everybody's thumbs up. Let's do it. All right. Now, at equilibrium, there's a certain amount of chlorine. When we add more chlorine, there's too much chlorine. And the equilibrium says, "Oh, wow, we've got too much chlorine. We've got to lower some of it." How can it reduce the chlorine? By shifting the equilibrium this way, where hydrogen reacts with chlorine. When something reacts, it's consumed. If you remember, when you consume a French silk pie, if you eat half of a whole one, you only have half left because you've consumed it, you have less. So that means immediately hydrogen concentration will decrease. Next, if you're reacting hydrogen and chlorine to reduce some of the chlorine, you're going to make more HCl because the equilibrium is going this way. And therefore, the concentration of HCl will increase. Now, when you put a reaction in an ice bath, what does it do? It removes heat. And now, if we look at this equilibrium, at equilibrium, there was a certain amount of heat. And now there's not enough heat. Oh, somebody stole my heat. Oh, woe was me. I need more heat. So how does it relieve that stress? It goes in this direction. Hydrogen and chlorine react to make more heat. Well, if that happens, once again, hydrogen is reacting. It will be consumed and you will have less. It decreases. Or you can use the arrow down if you don't want to write. Now, what happens to the HCl? Well, you're making more heat by shifting the equilibrium this way. Therefore, you're going to make more HCl. If you make more of something, you'll have a higher concentration and it will increase. And finally, the last one, and that is put it in a beaker of boiling water. What does boiling water do? Oh, look, someone was nice enough to write on the whiteboard. It adds heat. Well, at equilibrium, oh, I knocked out a chlorine accidentally. Hold on. At equilibrium, there's a certain amount of heat. When we put it in boiling water, there's more heat than should be. And now the equilibrium reaction says, oh no, I've got too much heat. I've got to get rid of this excess heat. I'm under stress. That's the Chatelier's principle. And how can it get rid of heat? Only one way. Heat reacts with HCl to go this direction. And it makes more chlorine and hydrogen. Now, if it makes more, if it first of all reacts, HCl reacts with heat. When something reacts, it's consumed. And when it's consumed, you have less of it. So the concentration for this part C will decrease. Now, what happens to the hydrogen gas? Well, if we look up here, hydrochloric acid and heat, hold on, that looks ugly. Now I feel better. Drives the equilibrium there to make more chlorine and hydrogen. That's how we reduce the heat. Well, if you make more of something, guess what? The amount you have, the concentration increases. So you're going to have more chlorine and more hydrogen. So what happens to the concentration of hydrogen? It increases. And this is an exothermic reaction. How do you know heat is on the right? The way it's written, this is called exothermic. That was fun. Let's do another one. But before we do, I see a question. Hold on. To open up a chat. Oh, Murray, Yes, I am set with for the winter, at least till January, maybe, hopefully longer. No, I'm not an alcoholic. I'm a teaholic. I got my big order of tea in too for the winter. All right, let's have fun with one more. All right, here we have carbon reacts with water and heat to give carbon monoxide and hydrogen. All right, let's look at the following. What happens to this equilibrium? What happens to water concentration and carbon monoxide if I add more hydrogen? B, put it in a beaker of boiling water, and C, put it in an ice bath. And let me just remind you, if I can remember it right. Eh, boiling water adds heat, ice bath removes heat. Have fun. When you're done, give me a thumbs up or say something to wake me up because I'm going to take a nap. Not really. And with the nice weather this afternoon, I'll probably mow my lawn for the last time this year. Yay. And tomorrow I get to swap out my sump pump pipes for the summer fall to the larger winter one. Yay, sort of. All the joys of owning a home. It's amazing with YouTube and Home Depot, there's just about nothing except major plumbing I won't, and heating I won't fix in my house or haven't fixed already. And when you're done, give me a thumbs up. While you're doing that, I'm looking out on the internet and see what's happening in the real world. All right, let's get back to the whiteboard. I assume everybody's done now. All right, let me get to work. All right, let's look at this. What happens to the water and carbon monoxide if I add more hydrogen? At equilibrium, there was a certain amount of hydrogen. Now you add more hydrogen, the equilibrium reaction says, oh no, I have too much hydrogen. How do I get rid of it? The excess? Well, carbon monoxide and hydrogen react. When something reacts, it's consumed. There's less of it. Well, if there's less hydrogen, there's going to be less carbon monoxide, CO. So this will decrease. Now, if these two react, they make more heat, more water, and more carbon. And therefore, what happens to the amount of water present? The concentration will increase. Next, what happens when we put the reaction, which is in a test tube, if you did it in the lab. If you look at the lab I went through on Tuesday and looked at the videos, you see that's what they do. If you put it in a beaker of boiling water, what happens? Oh, look, someone was nice enough to put here, boiling water adds heat. Well, at equilibrium, there was a certain amount of heat. Let me clean this up. Oh, I wiped out some of the heat. It's back. Well, at equilibrium, there was a certain amount of heat. When you put it in boiling water, now you have more heat. And the equilibrium says, and they actually, if you listen closely, it will say, oh no, I have too much heat. How do I get rid of all this? It's giving me a lot of stress. I'm going to use Le Chatelier's principle. The equilibrium shifts in this way. Why? Because when heat reacts with water and carbon, heat is consumed, there's less. Well, if water reacts with the heat, it also is consumed. Therefore, the amount of water, the concentration, will decrease. If I can spell it right, which I can't. Don't look. I said don't look. I was always the first one down in the spelling bee. Now, heat reacts with water to go this way to lower the excess heat. When it goes this way, you make more carbon monoxide and hydrogen. And if you make more of something, the concentration will increase. Again, spelling error, don't look. And that's what happens. Let's do C. Now in C, we put it in an ice bath. And look, someone was nice enough to write on the screen here, when you put something in an ice bath, it removes heat. Ice bath removes heat, boiling water adds heat. And at equilibrium, there was a certain amount of heat. And now putting it in the ice bath, you've removed it. If you listen carefully, the equilibrium starts saying, oh no, I don't have enough heat. I need more heat. Well, how can you get more heat? By carbon monoxide and hydrogen reacting and make more heat. When they make more heat, you make more carbon and water. So down here, what happens to the concentration of water? Well, if you're making more of it, it will increase. And what about carbon monoxide? Well, how did you make more heat and water? You reacted the carbon monoxide with hydrogen to go this way. Well, that means this was consumed. And when you hit consume something, use reacted in a reaction, you have less. Therefore, since you have less, the amount or concentration will decrease. And that's how you do Le Chatelier's principle. If you want to share this with other people, you can. If you don't, well, they should have been here. But anyways, on test 4, and I won't cut this out of the video, but they might miss it, but it's here. On test 4, historically, I put usually 9 to 12 points on Le Chatelier's principle, just like I just did. So I would highly recommend you do the practice problems. I'll have an announcement to make in a second.
Can I ask you a question, Dr. White?
Always.
On that ice bath?
Hold on. What?
On that ice bath, letter C, does that mean then that the reaction moved to the left?
Well, I never asked that, but let's take a look. And the answer is correct. If you call, okay. Hopefully you know this is left and this is right. Dr. White doesn't assume anything.
Correct, okay.
And that's why I said correct. So if you put it in an ice bath, it goes to the left. If you put it in a boiling water, it shifts to the right. Now, I don't like using that terminology because I've learned it confuses students. What I do try and do is show you how you can determine what happens to the amount, otherwise known as the concentration, of different reactants and products in the reaction.
Okay, thank you.
You're welcome. Remember, all questions are good questions. And I practice that. Now, just to remind you, in your lungs work by using Le Chatelier's principle. And it's either your kidneys or liver uses it too. I don't know which, because I'm a chemist, not a medical doctor or biologist. But your body uses Le Chatelier's principle. And a version of it, sort of the Chatelier's principle, keeps your blood at a certain measurement, which I'll teach you next chapter. Boy, all this chemistry going on in my body. And that's why I always laugh when you hear people say, I don't like chemistry. Well, I guess you don't like being alive either. What they really mean is they hated the way they were taught it. Like my sister. She doesn't like chemistry. All right. Equilibrium constants, we've done that. I'm going to skip this section. And guess what? We're finished with this chapter. Monday, I will go through the equilibrium chapter practice problems. Between now and then, I highly recommend you do them. And you know what this means? It's new chapter time. It's time to go back to do chapter 14, which in our book, if you bought it, should have been after chapter 15. And since it should have, guess what? Dr. White knows chemistry and changed the order. See how powerful I am? Able to change order of chapters in a single bound. And no, I'm not faster than a speedy train. For those who know the Superman legend. All right, everybody see, oh, hold on, don't get dizzy. Chapter 14, acids and bases on your screen. Thank you. Now, this chapter is about acids and bases. And of all the chapters this semester, I have to say, this is probably the most useful chapter for your personal life and maybe your professional life. So it's about acids and bases. Let me do one more quick check. Everybody see acids and bases on the screen? Thank you. All right. Now, if it's about acids and bases, what's an acid? What's a base? Well, it turned out for a long time, that was a very hard question to answer. And it was only until about, I may be off by 5 years, about 1910, oh, this is 100 years ago in the history of mankind, that's not long ago, that finally people came up with a good answer. Now, the first person to answer that question was Arrhenius. Click, switches off for the slide. And I'll explain why in a little while later today. Now, Arrhenius came up with a definition. An acid is a hydrogen-containing compound in water that produces what we call hydrogen ions H+. An example of this would be hydrochloric acid. If I take hydrochloric acid, this is actually an equilibrium, but the equilibrium is like 99% to the right, you'll get this, which is called the hydronium ion. This is another way of writing H plus chloride anion. And by the Arrhenius definition, this is an acid. Now, there's an Arrhenius base, and again, switches off on the slide, and that's a hydroxide. Hydroxide is OH minus, containing compound that in water produces hydroxide ions. Actually, hydroxide containing would be no charge. An example of that is sodium hydroxide. And this is dissociates like that. And the water is hydrating both of those. So if you produce H plus, acid and water. If you do it with OH minus hydroxide, chemical when you put into water forms that, it's a base. Guess what? There's a problem. What if you're not doing it in water? Is it an acid or base? Well, you can't use the Arrhenius theory. It's no good for that. And therefore, people had to find a theory that both under Arrhenius and water, what was an acid is still an acid, what's a base is still a base, but in non-aqueous, not water, solutions or systems, you still can define acid and bases. And turned out that took a long time for people to figure out, people meaning chemists. And someone did. But before we get to that, let's look at some acids that you should know, the formula for. Switches on. Let's try this again. Key acids you should know. Hydrochloric acid, you should know if I ask on a test, is HCl an acid or base? It's an acid. Now, this HCl, let's get personal. Now I'm gonna get real personal. HCl, guess what? That's the compound our bodies make in our stomach, and we call that stomach acid. And one of the, how should I say, for me personally, one of the great wonders or miracles of life is I, and so do you, have cells in our body, in our stomach, that produce hydrochloric acid. That this is, wow, I can do that. That's amazing. Now you know I'm a chemist. Now, the next acid is sulfuric acid, H2SO4. And this is sulfuric acid. Of all the chemicals made in the United States, the chemical that's made the greatest amount per year is sulfuric acid, H2SO4. It's used in many things in industry, and that's why it's the most important, one of the most important chemicals made in the United States. Now, one place you find sulfuric acid is, how many of you have ever looked at a car battery? You know, it's a big thing. In the old days, they had caps that you could take out and fill the fluid that's inside there if it gets low. Then they determined, well, if we seal it, you don't have to do that. What's the fluid inside? It's sulfuric acid and water. So all your car batteries have sulfuric acid in it. Now, when I was in high school, I helped my father change a battery in his car, and I wasn't careful. I got some of it on my clothes, my winter coat, and it ate a hole right through there because the acids will react with cotton and things like that. I learned a valuable lesson. Also, my mother was pretty upset with my father and me because I had to get a new winter coat. It was a nice coat, but it was now a holy coat. Holy cow. Look out, Dr. White's on a winning streak. All right, another important acid is nitric acid, HNO3. And it's used to make many things such as fertilizer, and it's also used with sulfuric acid to make explosives. Yep, there's good parts and bad parts. Now the last one, and I'll draw the actual structure, and this one you don't have to know, but I thought I'd teach you it anyways. This is how you write organic chemical formulas, structures. This is acetic acid, And I would bet almost all of you have acetic acid in your house. I don't have acetic acid in my house. I would know about that. Yes, you do. How do I know that? Well, if you take about 4% acetic acid and mix it with about 96% water, you'll get a homogeneous solution. We have a name for that. Vinegar. Vinegar is just a dilute solution of acetic acid. And they don't call it that. They call it vinegar because I don't know how many eons that name's been around. One of the things, weak acids, and I'll teach you what weak or strong have a very strong, almost bitter taste. And if you think about that, how many people you know do shots of vinegar? Hopefully none. And it has a, maybe not bitter, more of a sour taste. And certain ethnic foods like sweet and sour pork or sweet and sour meatballs if you're Swedish, or other sweet and sour dishes in different ethnic foods, you add certain mild acids. One of them could be vinegar. Another one is called acetic, citric acid, which you find in lemons and limes. But you didn't know there was acid in lemons and limes. Well, there it is. It's citric acid. So you should know hydrochloric acid is HCl, sulfuric acid is H2SO4, nitric acid is HNO3. I won't ask you to learn acetic acid. Let's do this. And test, if I put this down, I ask, is that an acid or base? You should know HCl acid. Same thing here, and same thing here. Now, what are some key bases? Well, probably one of the most important in our daily life is sodium hydroxide, and the old name was lye, and this is a base. How many of you have ever heard of lye soap? And what they used to do, our ancestors, and they still do, and by the way, I worked in a company that made lye soaps. They call them soup noodles. I don't know why they call them noodles, but they'd sell them, and we sold to places like Neutrogena and other places. But anyways, our ancestors found out if you boil animal fat, like beef fat, with lye, you'll get this white solid, and guess what? It cleans my hands and my clothes. And that's what your bar soap is in your bathroom if you use a bar soap. It's animal fat that's been reacted with sodium hydroxide. It's purified. No, it's not like pure any, you won't hear any moo or when you use your bar soap, but that's true. Now, another one is potassium hydroxide, KOH. And it's called potash because it was originally found in the ash of wood underneath your cooking pot. And that's how it got the name potash. And that's KOH. Now, ammonia, we've talked about it already, is a very strong base. Now, there's one last that you should know, and that's sodium bicarbonate. And you know that as baking powder. And that's the stuff you use when you cook and you want things to rise up. So on a test, if I put down NaOH and I ask you, is that an acid base or a salt? And I hope you know this is a salt. This is a base. KOH is a base. NH3 is a base. And NaHCO3 are all bases. And if I look at the clock, I've run out of bases. It's time to take a break. So, oh, that was late. But with that, let's take a 5-minute break. I'll see you in 5. I'm going to go stretch. right, let's get back to work. Sorry, I'm running a minute late. Time to begin again. I was making some tea for right after class. Stuff I have to. I'll have a nice fresh cup of tea waiting for me. I like to steep my tea so it's nice and strong. All right, we were talking about acids and bases. Remember, acid, you should know these acids. HCl, H2SO4, HNO3. And if on a test I ask, is this an acid or base, HCl? It's an acid. Same thing with sulfuric acid here and nitric acid. I won't ever ask acetic acid. But the next time you go to your refrigerator, well, I'm thinking of something else. Next time you go to your kitchen and pick up the bottle of vinegar, think about it. That's an acid, a weak acid. Now, just a quick sidelight. There are different types of vinegar, and they all have acetic acid and water, but they have some other things that give them flavor. My favorite one, besides regular apple cider vinegar, which I like a lot, is the Moroccan rice vinegar, rice wine vinegar, and that's really good stuff. And there are others. Get the gold label Moroccan. My local store, Valley, has it. I'm not sure if Jewel, I've never checked there. But all vinegars are acetic acid and water, plus some other flavorings like champagne vinegar or red wine vinegar, etc. And you should know, if I put down NaOH, is this an acid? Oops. Is this an acid or base? Oh, sodium hydroxide, it's a base. Now, the main drawback of the Arrhenius theory is what happens when you're not in water? Well, you're stuck. And that's not good because chemists do a lot of reactions with acids and bases that aren't in water. Dr. White, part of my PhD thesis, I used a very specialized base that I used in tetrahydrofuran. That's a chemical that's definitely not water. Well, how did I know it was base? Well, another theory. And two chemists, Bronsted and Lowry, independently, about the same time, let's do something. We got time? Yeah, we got time. All right, how come I don't see you? There you go. And if you look in Wikipedia, they have it. And here are the two chemists, Bronsted and Lowry. And as it says, see, Dr. White wasn't lying to you. Hold on, let me check. Everybody see the internet? Right here, HA plus B. Okay, thanks. And if you look, here's pictures of them. And when did they do this? 1923. Wow, that's even less than 100 years ago. I was off by 10, 12 years. What's the Bronsted-Lowry theory of acids and bases? Hold on. Dr. White should have closed this. And the Bronsted-Lowry acid-base theory was created because the Arrhenius theory does not explain acids or bases in non-aqueous solutions. Non-aqueous when there's no water present. If I had a dial that I could turn up to 10, I've just turned it up to 1,000. You should know this. The next couple of things are probably some of the most important things I'll teach you this semester. Now, what is a Bronsted-Lowry acid? It's anything, any substance that can donate a proton. A proton is H plus to something else. The most important thing you should know, what is a Bronsted-Lowry acid? It's a proton donor, H plus. It donates protons. If we're in a classroom, I'd do the following. If I were a Bronsted-Lowry acid, I'd say, here, take my proton, take my proton. I'm an acid. And if I was a strong acid, I'd say, here, take my proton, because I'm going to give it to you whether you like it or not. We'll talk about strong and weak in a little while. But a Bronsted-Lowry acid, proton donor, here, take my proton. Now, example of this would be hydrochloric acid. And the beauty of the Bronsted-Lowry theory of acids and bases, whatever was an Arrhenius acid is also an acid in Bronsted-Lowry. And that was not an easy thing to do. And this equilibrium, think of this as H plus, think of it, it's not really, but Cl minus. And the H plus goes to the water, and you get this H3O plus Cl minus. And C going this direction, HCl is a proton donor. Therefore, HCl is an acid. And that's how you know acids. In Bronsted-Lowry theory of acids and bases, it's an acid. Oh, let's do another one. And you can do this for other things that are not water. Again, this is an equilibrium, but it's mostly to the right. And think of this as H plus. It's not really, but think of it. And the H plus goes to the water. You form H3O plus because you've added an extra hydrogen plus it's got a plus charge. Plus, this is called the bisulfate anion. And now you know H2SO4 donated a proton, so it's an acid. How do you know? Because in the Bronsted theory of acids and bases, an acid is a proton donor. I'm an acid. Here, take my proton. I'm donating it to you. See what a nice acid I am? Well, that was hokey. Now, if this is an acid, a proton donor, what's a base? Well, a base is any substance that can accept the proton and from other substances. So you should know. I forgot to write this here. Oh, come on. You should know that a Bronsted acid is a proton donor. And you should know You should know Dr. White can't write today. What's a Bronsted-Lowry base? A Bronsted-Lowry base is a proton acceptor. And let's look at an example. If we look here, ammonia reacts with water to give NH4, and notice it's picked up H plus. Here it's 3, now it's 4, no charge, charge. So this is added H plus, it's accepted it. And we're to get it from the water. Now, if I'm a Bronsted-Lowry base, I'm a proton acceptor. If I'm a Bronsted-Lowry base, and if we were in a classroom at ECOD, I'd say, I'm a Bronsted-Lowry base. Come on, give me your proton. Give me your proton. I'll take it because I'm a base. Remember, Bronsted-Lowry base, proton acceptor. Give it to me. Come on, give me your proton. Now, Bronsted-Lowry acid, here, take my proton. You take it. Go ahead, take it. And that's still today the most prevalent definition and useful definition of what's an acid, what's a base. So if I ask on a test, what's a Bronsted-Lowry acid? And the answer is proton donor. If I ask on a test, what's a Bronsted-Lowry base? And the answer is a proton acceptor. Now, it turns out when water accepts a proton, hold on one second. Actually, it was more than 1 second, but hold on. When water accepts a proton, it forms this intermediate, or this chemical, H3O plus. And this is an actual molecule you can isolate, and it's called the hydronium ion. And it's very important to our daily life, the hydronium ion. Now, just to point out the Bronsted-Lowry theory of acids and bases, we look here, HCl will donate a proton to ammonia. NH3 becomes NH4 plus, this becomes Cl minus. Well, this is a proton donor. And you know, that's an acid. Now, the ammonia is a proton acceptor. And a proton acceptor is a base under the Bronsted-Lowry acids and bases. If you notice right here in this reaction, there's no water, which you would need for Arrhenius. Now, do I have time? Oh, I do. When you react ammonia and hydrochloric acid, you get a white solid, the NH4Cl minus ammonium chloride, a salt. Now, both of those chemicals can exist in a vapor gas form. Keep this a secret. A long time ago, in a galaxy far, far away, some guys in high school who were really good science majors, I don't know who they were, took some cotton balls. One of them they put hydrochloric acid on, the other they put ammonia on. They stuck it in a locker in the high school and put them close together, but not too close, and the vapor came out and reacted, and all of a sudden you saw this white, looked like smoke coming out of the locker. And they had to evacuate the school because they thought it was on fire until they found out it was. They never found out who did it. Don't try that at home. See what a bad influence I am on you? All right, now, there's a very important concept in acids and bases that's called the conjugate acid, conjugate base. Switches on. And you should know this. Now, proton transfer doesn't always happen 100%. And acid bases are equilibrium reactions. And now you know why I did chapter 15 before 14, because it makes no sense in the book they have, well, here's an equilibrium reaction. What's that? I haven't learned about those yet. What's in the next chapter? Come on. Doesn't make sense, doesn't make dollars either. Ooh, that was a funny. But anyways, aren't you glad I know how to fix things? And when you have an equilibrium like this, acid-base, notice on this side you have the acid. In chemistry, HA is an acid. B, aren't we original, is a base. Now, two species that differ by a proton are called conjugates. And if they're acids or bases, they can be conjugate acids or conjugate bases. Now, by convention, on the right of an equilibrium, these are called the conjugates. Now, let's look at this. Here I have HA, I have A minus. The only difference here is a proton, H plus. Remember, a proton is H plus. And if I look here, I have B, and here I have HB, and B and HB plus are conjugates. Remember, conjugates are two species that differ by only one proton. Now, when we go in this direction, what is HA doing to go to A minus? Is it gaining a proton or losing a proton? Now, students always get confused about this, so take a deep breath. Instead of worrying about H plus, just look at the number of hydrogens. Does it lose a hydrogen or does it gain? Is there a difference between two things by H? Don't worry about the charge. If you notice over here, we have HA and A minus, and they differ by H plus, so they're conjugate and acid. Here's the acid. Now, here's the conjugate. Going this way, HA has given up to go to A minus, H plus, or just think of hydrogen. Now B, and that means if it gives it up, it's an acid. Now B going to HB plus, just count the hydrogens as accepted or gained, H plus or H. And the answer is it's gained something, it's accepted it. And what's a proton acceptor? A base. Now, that's this direction. Now we have to figure out the conjugates on the right. Are these acids or bases? So let's look at A. A goes from A minus to HA. Just count hydrogens when you think of protons. Has it accepted or donated a proton? Well, picked up one, so it must have accepted it. What's a proton acceptor? A base. So that means A minus is called the conjugate base. Now, let's look at B. B goes, HB goes to B when we're going this way. Does HB going to be accept or give, donate a proton? Well, it lost this to go to here. Therefore, this is donating a proton, and it's something that donates a proton is an acid. And when it's on this side, we call it the conjugate acid. And it turns out this is important. And the conjugate base of an acid is the species that remains when the acid loses a proton, and the conjugate base of a conjugate acid of a base is a species formed when the base accepts a proton. The easier way is the way I just did it up here. Seaboard, for example. Well, I better get to work then. But I see a question. Hang in there. Oh, who's showing their dog? Remember in grade school when the teacher said, well, if you're going to show it to her, show it to the whole class. Teachers didn't do that to me because you never knew what I might bring. It'd always be science stuff that they didn't understand. Teachers didn't like me because I used to talk and say things. They had no idea what I was saying. I gave a talk in 5th grade on plane polarized light, and the English teacher had no idea what I was saying at all. She was definitely not a science person. By then I was. All right, let me get to work because I'm supposed to show you an example.
Dr. White, I have to leave right now. I'm going with my son to orthodontics appointment.
All right, well, you have a nice rest of the day and rest of the week. First of all, thank you for telling me. I'll just mark you absent, but no, I'm just kidding. But don't forget, Monday we'll have class at 10. And if you can't make it, you can watch the video, hopefully. And Tuesday we'll have a late start at 10:30. Monday, I'll be
10
going
o'clock.
through the equilibrium problem set. And Tuesday we'll do the lab because we're not going to have class on Thursday.
Okay.
You can show up, I won't be here.
It would be nice if you can repeat those conjugate those acid-base pairs, you know, those problems, because I'm just still confusing.
Well, guess what? Come to my office hours always, and you can go back and watch the video because I'm going to do a couple right now. Even though you're leaving, you can still watch the video.
Okay.
It's going to be an extra $19.95 for shipping and handling.
I see you on Monday from Florida.
All right, Florida. Ooh.
Yeah. Bye-bye, guys.
All right, I'll have to see what kind of tangents you get.
Bye.
Bye. Well, now I got to charge you 2 extra because this is private too. No, I'm just kidding. All right. Let me hang in there. There's a great textbook, which other school I use, called Chemistry by Karen Timberlake. I've actually in the past emailed Karen Timberlake to make suggestions in her book, and she's one edition, 1 or 2 before this copy, she actually did them. And what I'm looking for are some examples to do conjugate acids and bases. Because I had physical therapy this morning, I didn't have time to find these, but I know this book quite well, so I've used it enough times. Bingo. Hold on, Dr. White was looking at the wrong part of a problem. Did I tell you about the 10-second rule? When I'm writing things down, give me about 5-10 seconds in case I change my mind or make a mistake. All right, let's get going. And the question is 1 point each, 4 points total. Identify W, X, Y, and Z as acid base, conjugate acid, conjugate base for this reaction. Well, how do you do that? Well, the first thing you do is identify the conjugates. What differ by only hydrogen H+. Now, easy way to do it is look for other atoms. Notice in water, there's an oxygen. Is there an oxygen in Y, hydrogen cyanide? No. But in hydroxide, is there an oxygen? And the answer is yes. So, therefore, these are conjugates. Now, the only thing we have left is this and this. Is there a difference in this H+? Yes, because you get the H and the plus charge neutralizes the minus. Just think of hydrogen. You don't have to worry about plus or minus. So these are conjugates. Now, by definition, on the right side, Y and Z are always conjugates. Everybody with me? Now, let's look at what happens when you go from water to its conjugate. Z, hydroxide, has it gained a proton or lost a proton? Just count the hydrogens. That's 2, that's 1. Is that a gain or loss? Time's up. Hopefully all thought of it as a loss. It donated a proton, it lost one. What's something that's a proton donor? An acid. Everybody with me on that? How many would like me to do that again? Raise your hand. All right. Look at the conjugates. We decided that W and Z are conjugates. That means they differ by only 1 proton. Just look at the hydrogen. Students get all messed up when they think about charges. Here it had 2, here it had 1. Did it give it up or gain? Gave it up. Gave it up means donate. Ooh, I get to do this again. I do this in the classroom. And what's something that donates a proton? I'm a Bronsted-Lowry acid, because here, take my proton. Now, if we look at X, which is called cyanide anion, starting here to go to hydrogen cyanide, this has a gained or lost a proton. Just think of hydrogen. And here it had none. Here it's got one, so it's gained one, H. What's something that gains or accepts a proton? A base. All right, so we've got these done. Now, how do you go and do what is X and Y and Z? Well, let's look at Y. Why not? Look out, I'm in rare form today. Gotcha. But anyways, Y goes to X. Notice here it has a hydrogen. Oh no, here it doesn't have. It's actually H plus, it's lost. But here it's one, here it's none. Did it donate or accept H plus hydrogen? It's got one less, so it's donated it. Oh, I get to do this again. And what's a proton donator? Here, take my proton. It's an acid. But because it's on this side, it's called the conjugate acid. And that leaves us Z, which better be a conjugate base. Well, let's find out. If we look at Z, goes from this to water. Has it gained or lost hydrogen? H plus really, but think of it. Here it's got one, here it's got two. It's gained it, accepted it. And what's time for me to do this again. What's a proton acceptor? A base. Therefore, hydroxide, Z, going to water, W, accepted a proton. That makes it a base. And because of that, on this side, that would be conjugate. Remember, the conjugates are always on the right. I don't know who started that, but that's just the way chemists do it. That's the convention.
Can I ask a question?
Always.
For some reason, I cannot understand that last one, the Z. Are you looking at it from the OH going left to the H2O that it gained
All right.
an H?
Remember, this is an equilibrium.
Okay.
It can go this way and it can go this way. When we're talking about acid bases, we're talking just one direction. When things react to go to the product. Now, in an equilibrium, when it goes this way, the products are on this side. When it goes this way, the products are on that side. So if we're looking at hydroxide, is that an acid or base? When it reacts, we're looking at, hold on, I gotta clean up the screen a little. We're watching, saying when it goes this way, hydroxide, when it reacts with hydrogen cyanide, is it an acid or base? We already know it's on this side, it's conjugate, but just for you to help identify it. So, OH going to water, going this way. Is that picking up a proton or donating a proton? Picking up or accepting means it has more when it ends up on this side. So it's
I see it.
one hydrogen. Oh, I think I saw the light bulb go on over your head.
Yeah, I see it. Yeah, I get it now.
And there
I was doing it in the other direction and I kept saying it lost one, but I'm
when
going
you
this.
look at something, you gotta say when it reacts with the other species to go to the other side. In an equilibrium, it can go either this way or this way.
Yeah.
Or it goes
Okay.
actually both at the same time. But when you're deciding like W, is it an acid or base? You got to say when it reacts, it's going over to its conjugate. This way.
Thank you.
You're welcome. See, Dr. White isn't lying. All questions are good questions. But aren't you glad I also answer them too?
Yeah, thanks.
You're welcome. All right, let's do another one. Oops, hold on. That looks like a better 4. And I'm going to let you have some fun. Identify W, X, Y, and Z as acid, base, or conjugate acid, or conjugate base. Have fun. And since there are only a couple of us left, if you want to ask other questions, anything but what's the meaning of life, I haven't figured that one out yet, I'll be more than happy to answer any question, as always. And with the nice weather, even though it is windy out there, like I said, not that I'm looking forward to it, but I'm glad it's probably the last time I will mow my lawns this afternoon. And again, 4 points, 1 point for each one being right. Hint, hint. Wonder if people misinterpreted the lab where it said Thanksgiving, no lab. They should have realized today's not Thanksgiving. See someone come to class next week and say, you know, it's because of you I cooked a turkey last Thursday. I hope not. When you're done, give me a thumbs up. You can do it on video too. All right, let's do it. First thing I like to do is find out where the conjugates. Those are species that differ by H+. This has the nitrogen, no oxygen. This has the nitrogen, no oxygen. Notice this is NH3, NH4+, so this is a conjugate. Whoa, ran off screen there. Now, this has 3 oxygens, this has 3, a nitrogen, nitrogen, H, no H. This is a conjugate, okay? Now, remember, on the right, these are always the conjugates. That's the convention. Don't ask me why. That's just the way it's always been in my life, and somebody made that decision. Now, let's look at W. When W goes to its conjugate Y, going this direction, does it lose or gain a proton? Just count hydrogens. Here it's got 3, here it's got 4. Is that an increase or decrease? And time's up. Hope we all picked increase. What's something that accepts a proton? It's a base. So ammonia is a base. Now let's do HNO3. Goes from X to Z. Here it has a hydrogen. Here it's lost a proton, no hydrogen. So has it gained or lost a proton? And it's lost. It's donated. When it loses, we also say donate. And what's a proton donor? That's an acid. Well, I'm half done. Now, let's go to this side. Now, we look at the reaction going that way. When Y goes to its conjugate, W, does it donate a proton, give it up, have left, or have more? Here we got 4, I'm sorry, trying to confuse you. Here we have 4, it goes to 3, so it's got 1 less hydrogen, really proton, but I find students find it easier, just count the H's. And what's something that gives up or donates a proton? An acid, and it's on this side, so that makes it a conjugate acid. Now, we've got 1 left to go, and that's when we're going in this direction. We go from Z to its conjugate, and that's why it's important to figure out the conjugates. X, does it gain or lose a proton? Just count the hydrogens. Here it has none, here it has 1. So is it lost or gained? Gain means accepted. And if I accept a proton, what am I? I'm a base. And that's how you do it. Now, it's important to remember, under the Bronsted theory of acids and bases, an acid is a proton donor. Under the Bronsted-Lowry theories of acids and bases, a base is a proton acceptor. Again, we're talking about H+. And this is something you should know. Acid, proton donor. Base, proton acceptor. Guess what? You have hydrochloric acid in your stomach. It's a proton donor. Is hydrochloric acid an acid or base? And I just gave it away. It's an acid. And if you took my Chem 170 at another school, or 1212, which I don't teach here anymore, I'm not going to go into why, but unfortunately I don't, you'll find out I would teach you how that acid breaks down the important food groups: carbohydrates, fats and oils, and proteins. But really the important food groups: French fries, pizza, vodka. Now you could throw in salami sticks and a few other good food groups, but that's that. All right, I'm going to do something unusual. I'm going to end a couple minutes early. Don't tell the dean, but this is a good place to break because I know how to teach. And with that, I'm going to say thank you for stopping by. I hope you had a nice morning with Dr. White. It's time for me to say Goodbye. Gang gesund. Be healthy. Be careful out there. Wear your mask. Wash your hands a lot. And I'll see you on, remember, Monday we'll have class at 10 o'clock. I'll be going through the equilibrium problem set. We're on track to finish. If you notice, I don't have to rush, which is a good thing. With that, I'll say goodbye, gang gesund, be healthy, have a nice rest of the day, rest of the week, and I'll see you on, remember, Monday.